Hello Math 1093, this is Dr. P with Adding the Unknown. So I've put up an example problem here. We're given two angles, alpha and beta, and we're given the sine of alpha, but other than that, only the quadrant that alpha lies in. It's this one right here. That's quadrant 2. And we're given the cosine of beta, it's 5/13. And we know which quadrant beta lies in, it's quadrant 1. But other than that, we don't know very much about alpha and beta. And we're asked to find the values of cosine of alpha plus beta and then cotangent of alpha plus beta. And we're going to illustrate how we can do this using sum of angle identities. Now, we don't know anything much right now about alpha plus beta directly. Like, we could probably make a guess about where it lies approximately, but we don't know exactly where it is, and we don't know any of its trig function values right now. Same with this cotangent here. We don't know where alpha plus beta is exactly, so we can't find these values directly. But we can use the fact that cosine of alpha plus beta is expressible in terms of cosine of alpha, cosine of beta, and sine of alpha, and sine of beta, because that's the sum of angles identity for cosine. So we're going to use that formula to figure out the value of cosine of alpha plus beta. And you know that we're on the right track here because we have some of the info that we need to find this, to find the value of this expression. Sine of alpha, we know it is 3/5. Cosine of beta we know is 5/13. That's a good sign. But we don't know quite yet what is the cosine of alpha and what is the sine of beta. We're going to have to figure those out somehow. But you may remember from our past work in this course that given the value of one trig function at an angle and given what quadrant the angle lies in, we can find the other values of the trig functions of that angle. So that's what we're going to do here. We're going to use a little geometry to do that. So I want to draw a circle here. Not decide just yet what its radius is going to be. Man, that's a really bad coordinate plane. It's very crooked, very Simpsons-ish. Anyway, so we're going to draw a circle here. We're going to try and draw alpha. We know that alpha has a sine of 3/5. So what does that mean? I'm going to take the y over r interpretation of sine alpha here and say that this circle is going to have a radius of 5. So let's mark that off. Let's say r is 5. And this point is going to have a y coordinate of 3. All right, so I'm going to mark a point in here that's at about the right spot. That radius is going to be 5, and we know that its x coordinate is, well, we'll just call it x for now, and its y coordinate is 3. That would be alpha. Okay, how are we going to find x? We're going to use the Pythagorean relationship. We know x squared plus y squared has to equal r squared. We know that r is 5. We know y is 3. And we want to find x squared. So x squared needs to be 25 minus 9, which is 16. So x has to be plus or minus 4. And in this case, because we were given that alpha is in the second quadrant, we know x is going to have to be -4. So that means that cosine of alpha is going to be -4/5, which I'll just rewrite as -4/5. So that's cosine of alpha, and that's going to be -4/5. Okay, what about beta, sine of beta? Same strategy. We're going to draw a circle. And you don't have to do the circle drawing part quite this early. Oh wow, that shaped up to be a really nice circle actually, compared to most that I draw on this tablet. Anyway, we're given that cosine of beta is 5/13. We'll take the x over r interpretation of that. So we're going to let x equal 5, let r equal 13, so let the radius of this circle be 13. We're given that beta is in the first quadrant here. By the way, I might not have said it earlier, but the reason I drew the angle off in this direction in the first example is that I was given alpha was in the second quadrant. I have to pay attention to that. Beta is in the first quadrant, so I'm going to draw an angle over in the first quadrant whose cosine looks like it might be 5/13. In other words, I'm going to draw a radius of 13, and hope that the x coordinate there comes out to be about 5. And its y coordinate we'll have to figure out. So again, I'm going to use the fact that x squared plus y squared is r squared. And then we know x is 5, so 5 squared plus y squared has got to be 13 squared. So 25 plus y squared will need to be 169. Y squared is 144. So y is either plus or minus 12. In this case, we know we're in the first quadrant, so y has to be 12. So that means that sine of beta will need to be what? It needs to be y over r which is 12 over 13. Okay, so we know that sine of beta is 12 over 13. And now we have all the little ingredients that we need to finish off finding the value of this expression here. So cosine of alpha plus beta is going to be negative 4/5 times 5/13. So that's kind of nice how that worked out. I actually didn't even intend to do that. Minus sine of alpha, that's 3/5 times sine of beta, that's 12/13. All right, now we just have a little work to do here. Actually, I have the feeling that this 65 down here is not going to get canceled by anything up here. So I'd probably better not cancel these 5s. Probably better just leave that as negative 20 over 65 and just leave that be. And then that's minus 36 over 65. And that comes out to negative 56 over 65, which is hardly an elegant looking answer, but I think that actually is the cosine of alpha plus beta. Now, does that make sense? Does that even seem plausible here? Because I got these, now I have these pictures of two angles. I've got alpha over here, and I've got beta over here. There we go, that's beta. And if I were to add these together, would I get some angle whose cosine looks like actually pretty close to -1. Negative 56 over 65 certainly qualifies as being close to -1. Well, if I were to visually add these two angles together, so I'm just going to imagine taking this angle here, which is pretty close to 90 degrees, and add this on top of alpha. So how do I add two angles? Well, I traverse one angle, and then I traverse the other one. And I'm going to end up somewhere over here. Okay, so that's going to be beta there. And alpha plus beta is this entire angle right here. This whole thing. Whoop. Okay. So if I come out here, my x-coordinate is negative. And in this picture, it doesn't look like it's that close to -1. It doesn't look like it would be negative 56 over 65. But I think that is just a flaw in how I drew the picture. All right, so now I want to move on to the issue of what is cotangent of alpha plus beta. So this other problem here. Okay, there are a couple of ways that we could approach this actually. One way would be just to view this as an angle, alpha plus beta, and then work with the fact that cosine of alpha plus beta is negative 56 over 65, and kind of do the same routine that we did here. Create a triangle or create an angle in an appropriate circle, and then find x, find r, find y, and then use that to get the cotangent. But I'm going to illustrate one other technique here that might be useful at some point, and that is we're just going to find this directly using another sum of angles formula here. Okay, so what I'm going to do is I'm going to write down, okay, what is cotangent of alpha plus beta? Now I know that we never talked about a sum of angles identity for cotangent, but that's because once you have sum of angles identities for sine, cosine, and tangent, you have them for the other three. You just don't necessarily realize it. Because cotangent of alpha plus beta, what is that? That is 1 over tangent of alpha plus beta. And we do have a formula for that. The formula for that is, okay, it's a big fraction, so I'm going to put it under 1 for now. That formula is tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. Okay, and actually I love the fact that we're doing this way because this gives me the chance to remind you something important about fraction division. This is 1 divided by a big fraction. If you divide 1 by a big fraction, that's the same as multiplying 1 by the reciprocal of that fraction. So it's going to be 1 times 1 minus tangent alpha tangent beta over tangent alpha plus tangent beta. And once you see that, you realize the 1 doesn't really matter all that much. It's just 1 minus tangent alpha tangent beta over tangent alpha plus tangent beta. Okay, but now I'm like, wait a minute. Do I even know what tangent of alpha and tangent of beta are? If I knew that, I'd be pretty much done here. I'd just be calculating numbers. But do I have that information? Well, I do remember that when I talked about alpha and beta earlier, I did come up with sines and cosines for them. And if I have sines and cosines, or if I have x's and y's, I can get tangents. So let's just review what those are. Let's see. So what do I got here? For alpha, I know that tangent of alpha would be y over x for that angle. And I found y over x. Y was 3. and x was -4. There they are in nice close proximity. So tangent of alpha is 3 over -4. That's -3/4. Okay, so I'm just going to keep that value in mind. I'm not going to try and drag it up there because I feel like whenever I drag stuff on this, I end up dragging the entire picture, and I don't want that. For this angle beta, tangent of beta is equal to y over x. Let's see, where were y and x? Y was here, it was 12, and x was 5. So tangent of beta will be 12 over 5. Okay, so trying to remember those two values. Okay, think fast. -3/4, 12/5. Here we go. -3/4, 12/5. Okay, let me just record those here. Tangent of alpha was -3/4. Tangent of beta, 12/5. All right, let's substitute those in. So I got 1 minus -3/4 times 12/5, and we're over -3/4 plus 12/5. And, oh brother, okay, now I have to do all this arithmetic. This was poor planning on my part. Probably should have made this problem a bit easier. Okay, we always seem to get into these, but oh well. 1 minus, let's see, that's -36 over 20. And then on the bottom I have, let's see, I'm going to put everything in 20ths, get a common denominator. So I got -15 over 20. And then, oh, what is that? That's 48 over 20, I think. Boy, this is going to be quite the adventure. All right, so let's see. Up top I have 56 over 20, because that's just 1 plus 36/20ths. And then downstairs, I believe I have 33 over 20. All right, still with me? And then, again, ours is not to question y. Ours is to invert and multiply. I mean, really, usually I like to question y, but we got this fraction arithmetic embedded in what was already kind of a complicated example. So I'm just going to invert and multiply. And that gives me 56 over 33, which should be a little bit reassuring to us. Because, remember, this was supposed to be the cotangent of alpha plus beta. And the cotangent of anything is that endpoint's x-coordinate over the y-coordinate. And you see that we have this 56 here. And earlier we found that the cosine was -56 over 65. So I think that this is consistent with the idea that that x-coordinate is going to be probably -56. I mean, that negative gets buried in here because the y is also negative. So I think if I had to guess, if I drew this on a circle of radius 65, I would have an x-coordinate of -56 and a y-coordinate of -33. Just doing a little sense making on the answer there. Okay, that was kind of a complicated one. In the next video, we're going to talk about how to do this when someone throws inverse trig functions at us, and that'll be the end of this lesson.